Welcome to today's podcast. If you've ever wondered what Docker containers are, how they work, and why they're important for modern application development, you're in the right place. In this episode, we're breaking down Docker containers in the simplest terms possible. Whether you're new to Docker or just curious about what it can do, we're here to help you understand how containers can make your software more efficient, scalable, and easy to manage. So sit back and let's dive into the world of Docker containers. How does that sound to you?
Perfect. Okay, so now my first question is, now I have used computers, I have installed operating systems, and I know what an operating system is. So from that point, can you take me forward into the world of servers and then to Docker containers?
Great question. Let's start from where you're familiar. Operating systems. When you install an operating system, you're essentially setting up the core software that manages all the hardware, applications, and resources on your computer. This is crucial because it allows programs to run and interact with the hardware. Now, when you move into the world of servers, think of a server as a powerful computer that's always running, dedicated to handling tasks for other computers or users. Servers can run web applications, databases, or other services. Just like your personal computer, servers have operating systems, but they are optimized to handle many tasks at once and usually for many users. However, a problem arises when you need to run multiple applications on a single server. Traditionally, this would require setting up each application separately, making sure they don't conflict with each other, and managing them individually. This is where virtualization came in. Virtual machines, VMs, allowed you to run multiple operating systems on one physical server, but VMs are heavy. They require their own full OS installation, consuming a lot of resources. Now here's where Docker containers come in. Think of Docker as a lightweight, more efficient alternative to virtual machines. Docker containers package an application and all of its dependencies into a single unit, which can run consistently on any environment, whether it's your local machine or a remote server. Unlike VMs, containers don't need a full OS. They share the host machine's operating system kernel, but remain isolated from each other. This means you can run multiple containers, each with different apps, on the same server with much lower resource overhead. Does that explanation help connect the dots for you?
Yes.
Want to explore more about how Docker containers work under the hood?
Yes, so let me summarize what you have said. You said first that virtualization allows us to run multiple operating systems on the same computer so that we can run multiple applications, but these virtual machines need full operating system installed and they are more resource intense, whereas in case of...
Exactly, you've got it. Virtual machines each need a full operating system, which makes them heavier and more resource intensive. This allows for multiple applications to run in separate environments, but the cost is that every virtual machine carries its own OS, taking up more CPU, memory, and storage. Would you like to add anything more to that? Or should we move on to the next part, where we explore how Docker solves this?
Yeah, just a moment. So now, in order for Docker to run on a server, what do we need? So you can take us forward.
Great question. To run Docker on a server, you only need a few things, and they're relatively straightforward. First, you need a host operating system. This can be Linux, Windows, or Mac OS, but Docker is most commonly used on Linux servers because of how efficiently containers interact with the Linux kernel. The host OS is where Docker will be installed. Second, you need to install the Docker engine. This is the core software that allows you to create and manage Docker containers. The Docker engine works by running on the host OS and handling container creation, resource allocation, and isolation. It's what makes containers possible. Once Docker is installed, you're ready to run containers. Docker containers don't require a full OS because they share the host OS's kernel. What you do need is an image, essentially a blueprint of your application and its dependencies. Docker images are like templates. And when you start an image, Docker creates a container from it. Here's a quick flow. 1. Install Docker on the host OS. 2. Pull or create a Docker image, which contains your app and its dependencies. 3. Use Docker to run that image, which creates a container. 4. The container then runs the app in isolation, but using shared resources from the host. And that's pretty much it. Once Docker is installed, you can run multiple containers on the same server, each with different applications, without needing a full operating system for each one. Would you like to dive deeper into how Docker images work? Or how containers are created?
Yes, but before that I have a question. I know an Nginx web server. Can you give an example of how I can customize the Nginx web server by adding my own sample web page into it and create a Docker image and then run a Docker container using my customized Nginx server?
Great question. Let me walk you through a simple example of customizing an Nginx server with your own sample web page, then creating a Docker image from that, and finally running it as a container. Here's how it goes step by step. 1. Prepare your custom web page first. create a directory on your machine where you will store your custom HTML page. Let's say you create a directory called MyNginx. Inside this directory, create a simple HTML file. Here's a basic index.html. 2. Create a Docker file. In the same MyNginx directory, create a file called Docker file. The Docker file defines the steps to build your custom Docker image. Here's what your Docker file would look like. Let's break this down. From Nginx latest tells Docker to use the latest version of the Nginx image as the base. Copy index.html//share, and HTML copies your custom HTML page into the directory that Nginx serves HTML. Expose 80 tells Docker to expose port 80, which is where the Nginx server will listen for web traffic. 3. Build your Docker image. Once you've created the Docker file in index.html, open a terminal, navigate to your MyNginx directory, and run the following command to build the Docker image. Here, mycustom.nginx is tagging your image with the name mycustom.nginx. The dot represents the current directory, which contains the Docker file in index.html. Docker will pull the official Nginx image if it hasn't already, copy your HTML file, and build a custom image. Run your custom Nginx Docker container. Once the image is built, you can run a container based on this image. Let's break this down. MySD runs the container in detached mode in the background. 9SP8880 maps port 8080 on your machine to port 80 inside the container, so you can access the web server on your machine's port 8080. Name MyNginx container gives your container a friendly name, making it easier to manage. MyCustom.nginx is the name of the image you built. 5. Access your custom web server now. Open your web browser and go to localhost 8880. You should see your custom web page with the message, "Welcome to my custom Nginx web server." Stop and remove the container, optional. When you're done, you can stop and remove the container with these commands. You can see the code in our conversation history. That's it. You've now created a customized Nginx web server in Docker, built your own Docker image, and ran it as a container. Would you like to dive deeper into any part of this process?
Yes, can you also explain what is a Docker registry and how can I put my images in there?
Absolutely. Let's dive into Docker registries and how you can store your images there. What is a Docker registry? A Docker registry is a place where Docker images are stored and managed. Think of it as a repository for all your Docker images, just like GitHub is for code repositories. This allows you to store, version, and share your Docker images with others, or pull them down to use on different machines or servers. The most well-known Docker registry is Docker Hub, which is the default registry Docker uses. However, you can also use private registries like Amazon ECR, Elastic Container Registry, Google Container Registry, or even set up your own private registry. How does a Docker registry work? Pushing images. You can create Docker images on your local machine and push them to a registry so that they're available for you or others to pull down later. Pulling images. You can pull images from the registry to any machine where Docker is installed and use those images to run containers. How to put your images in a Docker registry, using Docker Hub as an example. 1. Create a Docker Hub account. First, go to Docker Hub. Please open your app to see this link and create an account if you don't already have one. You'll use this account to log in and manage your images. 2. Tag your Docker image. Push an image to a Docker registry. It needs to have a tag that corresponds to the registry and your repository name. If we continue with the previous example, where you created a custom Nginx image, you can tag it for Docker Hub like this. Here, replace your Docker Hub username with your actual Docker Hub username. The tag helps Docker know where to store the image in Docker Hub. 3. Log into Docker Hub from the terminal. You need to log into Docker Hub from your terminal, so Docker can authenticate your push command. Use the following command. You'll be prompted to enter your Docker Hub username and password. Once authenticated, you're ready to push your image. Push the image to Docker Hub. Now that your image is tagged and you're logged in, you can push the image to Docker Hub using the following command. Docker will take care of uploading the image to your Docker Hub repository. Once it's uploaded, you can view the image in your Docker Hub account under the repository section. 5. Pulling the image from Docker Hub later, or on another machine, you or anyone else can pull the image from Docker Hub using. This command downloads the image from Docker Hub and allows you to run it as a container, just like any other Docker image. Using a private registry, optional. If you want to use a private registry, such as AWS ECR or your own hosted registry, the process is very similar. 1. You'll need to set up the registry and get the credentials. 2. Use a similar login and tagging process, but you'll specify the registry's URL instead of Docker Hub. 3. Push the image to that private registry. For example, to tag for a private registry, it might look like this. And to push, a Docker registry is where your Docker images are stored and managed. You can push your custom images to a public registry like Docker Hub or to a private registry. Once uploaded, those images can be pulled down and run on any machine with Docker. Would you like to explore setting up a private Docker registry or more about advanced image management?
No, that is fine. See, now I have a question. for Nginx, I know now how we can deliver a static HTML page. But what about a Python application? Can you just explain how I can containerize a Python endpoint? A simple, tiny example using Fast API.
Great! Let's walk through how to containerize a simple Python application using Fast API, a modern Fast, hence the name, web framework for building APIs in Python. We'll create a basic Fast API app, containerize it using Docker, and run it as a Docker container. Here's how to do it step by step. Create a simple Fast API app. First, let's set up a basic Fast API app. In a directory called my Fast API app, create a file called main.py. Here's the code for a simple Fast API application that exposes a single endpoint. This creates a single root endpoint that responds with a JSON message. Message, hello from Fast API. Set up your dependencies. Fast API requires a few dependencies, including Uvicorn to run the application. So in the same my Fast API app directory, create a file called requirements.txt and add the following. Create a Docker file. Now that you have your Fast API app, you need to create a Docker file to containerize it. In the same directory, my Fast API app, create a Docker file with the following content. You can see the code in our conversation history. Let's break it down. From Python 3.1 to Slim, we use the official Python image as the base. Slim means a minimal version of Python. Worked app sets app as the working directory inside the container. Copy app copies all the files from your current directory into the /app directory in the container. Run pip install installs the Python dependencies listed in requirements.txt. Expose 8000 exposes port 8000, which is the default port for Fast API. Command uvicorn mange mass host 0.0.0.org 8000. This command runs the Fast API app using uvicorn, specifying the host and port. Build your Docker image. Now that the Docker file is set up, build a Docker image. Open a terminal in your my Fast API app directory and run the following command. This builds the Docker image and tags it with the name my Fast API app. Run the Fast API app in a container. Once the image is built, you can run it as a container. Here's what this does. Runasd runs the container in detached mode in the background. P 8000 maps port 8000 on your local machine to port 8000 inside the container, allowing you to access the Fast API app. Access your Fast API app now. Open your browser and go to /localhost 8000. You should see the following JSON response from your Fast API app. Fast API also automatically generates interactive API documentation. You can access it by visiting localhost 8000/doc, and you'll see an automatically generated Swagger UI where you can test your endpoint. Stop and remove the container, optional. If you want to stop and remove the container when you're done, you can run these commands. You can get the container ID by running. Summary. 1. Create a simple Fast API app in Python. 2. Write a Docker file to containerize the app. 3. Build a Docker image using Docker build. 4. Run the container using Docker run, mapping ports to access the API. 5. Visit localhost 8000 to interact with the API, and localhost 8000/docs for API documentation. Would you like to go into more details about any specific part, like working with environment variables or optimizing the Docker file?
No, I need to know now how can I put it online so that this can be shared with the public.
Great! To put your containerized Fast API app online so others can access it publicly, you'll need to deploy it to a server or cloud platform. Let me guide you through a common approach using DigitalOcean and Docker. Alternatively, you could use services like AWS, Google Cloud, or Heroku. But for now, we'll focus on deploying with DigitalOcean. Here's how to put your Fast API app online step by step. Choose a hosting provider. You'll need a hosting provider where you can deploy your Dockerized app. For this example, use DigitalOcean, which offers easy deployment of Docker containers on Cloud Droplets, virtual machines. Create an account at DigitalOcean. Please open your app to see this link. Set up a new droplet. DigitalOcean's term for a virtual private server. You can use the Docker one-click droplet, which comes pre-installed with Docker. Choose a location closest to your audience and a basic plan to start. 2. Set up your droplet. Once your droplet is created, connect to your droplet using SSH from your local machine. You'll need to use the terminal for this. Replace your droplet IP with the public IP address of your droplet. 3. Transfer your Docker image. Option 1. Build on the server. If you want to build your Docker image directly on the server, you can clone your Fast API project from a Git repository or transfer your project files using SCP. Then SSH into the droplet and navigate to the project directory. 4. Run your Docker container on the server. Now that your image is built or transferred, you can run the container on your droplet. Here's what happens. NISD runs the container in detached mode, background. NISP 8000 maps port 80, public HTTP port, to port 8000 inside the container. This allows people to access your app using your droplet's IP address. Access your app via public IP. Your Fast API app should now be running on the public IP of your droplet. You can test it by entering /your droplet IP in your browser. If everything worked, you should see the JSON response from your Fast API app. 6. Set up a domain name, optional. If you want to make the app accessible through a domain name instead of an IP address, register a domain using a domain registrar, such as GoDaddy, Namecheap, etc. Set the DNS, a record for your domain, to point to your droplet's IP address. Once the DNS propagates, usually within a few minutes to a few hours, you can access your app through the domain name. Install SSL for HTTPS, optional. If you want your app to be accessed securely over HTTPS, you can set up SSL using Caddy or Let's Encrypt. DigitalOcean has tutorials on this, but the general steps are: 1. Install Certbot on your droplet, Let's Encrypt client. 2. Get an SSL certificate. Certbot will automatically handle renewing the certificate. Alternative option: use Platform as a Service, PaaS. If managing a server feels too complex, you can use a PaaS solution like Heroku or Render, which simplifies deployment. Heroku supports Docker and is free to start. Render, a bit more powerful, and also supports Docker images. You just push your Docker image or Python code to these platforms, and they handle scaling, SSL, and domain settings for you. Summary: 1. Set up a cloud server like a DigitalOcean droplet. 2. Transfer and build your Docker image on the server. 3. Run your container exposing it on port 80, or access it via the public IP, or set up a custom domain. Optionally, add SSL for secure access. Would you like help with specific details, like setting up SSL or using an alternative hosting platform?
No, I think that is it. Thank you so much. Now I have one question. If I use Caddy, do I need to use Certbot?
Great question. If you use Caddy to handle your web server and SSL, you do not need to use Certbot. Caddy has automatic SSL management built in, so it will handle obtaining and renewing SSL certificates for you through Let's Encrypt without any extra configuration or tools like Certbot. Here's why. Caddy automatically provisions and renews SSL certificates for any domain you configure. You just point your domain to your server, and Caddy takes care of the rest. It's extremely convenient because you don't need to worry about manually installing or renewing certificates. Here's a basic Caddy file configuration example for a Fast API app. Caddy will: 1. Automatically get an SSL certificate from Let's Encrypt. 2. Set up HTTPS for your domain. 3. Reverse proxy requests to your Fast API app running on port 8000. In short, Caddy handles SSL for you, so there's no need to use Certbot when you're using Caddy. Would you like more details on configuring Caddy with Docker?
No, I have another question. Now, this is about running a simple application on one droplet. But how about scaling? Can you just introduce me to scaling, running multiple copies of the application so that we can deliver a larger audience?
Great question. Scaling your application is all about running multiple copies or instances of your application to handle larger traffic and ensure high availability. This is especially important when your app grows, and a single instance can't handle the load by itself. Let's break it down into 2 parts: horizontal scaling and vertical scaling. 1. Vertical scaling. This is the simplest type of scaling. It involves increasing the resources, CPU memory, etc. of your existing server to handle more traffic. However, there's a limit to vertical scaling. Eventually, even a more powerful server can't keep up with demand, and you'll need multiple instances of your app. Horizontal scaling. Horizontal scaling is more flexible and powerful. It involves adding more instances of your application or nodes across multiple servers or containers. This approach is what you'd use to handle larger audiences. Here's how you can achieve horizontal scaling in Docker, using Docker Compose for scaling. If you're using Docker, one simple way to scale is by running multiple replicas of your Fast API app. Docker Compose allows you to easily define the number of replicas you want to run. Let's modify the Fast API example with Docker Compose for scaling. 1. Create a dockercompose.yml file in your project. You can see the code within our conversation history. Here's what's happening. Replicas 3. This tells Docker Compose to run 3 instances of your Fast API app. Docker Compose handles load balancing between these instances automatically. To scale your service, just run. This command starts 3 replicas of your Fast API app, automatically spreading the load across those replicas, using Docker Swarm or Kubernetes for scaling. If you need more advanced scaling and orchestration, you can move from Docker Compose to Docker Swarm or Kubernetes. Both are powerful tools for orchestrating containers, scaling them, and managing high availability. Docker Swarm. Docker Swarm is Docker's built-in tool for container orchestration, and it's relatively simple to use. Swarm allows you to create a cluster of nodes and manage them as a single unit. It handles load balancing and scaling across nodes. To initialize a swarm, run, then deploy your app with replicas. This will create 5 replicas of your Fast API app, distributing them across the available nodes in your swarm. Kubernetes. For even more complex scenarios, Kubernetes is the go-to solution. Kubernetes is a robust container orchestration platform that automates the deployment, scaling, and management of containerized applications across clusters of machines. Here's a simplified flow of how you'd scale a FastAPI app with Kubernetes. Define your FastAPI deployment in a YAML file. You can see the code in our conversation history. After setting up a Kubernetes cluster, you'd apply this configuration. You can see the code in our conversation history. Kubernetes will handle scaling and load balancing automatically. Kubernetes also provides tools for auto-scaling, where it will increase or decrease the number of instances based on CPU or memory usage. This makes it ideal for handling unpredictable traffic. Load balancing. When you scale your app horizontally, you need a load balancer to distribute incoming requests across the multiple instances of your app. Many orchestration tools like Docker Swarm and Kubernetes have built-in load balancers. You can also use external load balancers like Nginx or HapProxy. Auto-scaling. As your traffic increases and decreases, you might not want to manually adjust the number of instances. This is where auto-scaling comes into play. Tools like Kubernetes and cloud providers like AWS or Google Cloud offer auto-scaling services that automatically add or remove instances based on traffic or resource usage. Summary. Horizontal scaling involves running multiple instances of your app to handle more traffic. Docker Compose can handle basic scaling by specifying replicas. For more advanced scenarios, Docker Swarm and Kubernetes are powerful tools for orchestrating containers and scaling automatically. Load balancing is necessary to distribute traffic across instances, and auto-scaling can automate this process. Would you like to explore Docker Swarm or Kubernetes in more depth, or focus on auto-scaling strategies?
No, this is it for now. I'll come back again. Thank you so much.
You're very welcome. I'm glad I could help. Feel free to reach out anytime. Take care and bye for now.